I'd like to consider about the long gamma ray burst associated with supernova explosion. So only, as you know, only small fraction of supernova can produce gamma ray burst. We don't know how it is, the central engine is working, but many people are considering that something is happening at the center of the massive star, and magnet or black hole may be produced at the center, and the jet is launched, and when the jet breaks out the progenitor star, and if you see the jet from this position, this jet is observed as gamma ray burst. This is what many people are considering, but this is just an animation, computer graphics. So we need to confirm this picture by realistic numerical simulation. Okay, I'd like to review the history of the numerical study on the central engine of gamma ray burst, long gamma ray burst. This is not so long, because partially first report on the association of a gamma ray burst with a hypernova was done in 1998. So not so long history. So, and the outline as Professor Kuma talked yesterday, outline of explosion mechanism is still under debate. And we don't know whether black hole or neutron star is formed at the center. Also, we don't know the key process to drive a gamma ray burst jet. Maybe neutrinos or maybe magnetic field. So there are several promising scenarios, like rotating black hole with neutrino heating, or rotating black hole with strong magnetic field, or rotating neutron star with strong B fields. So there are some numerical study. And this is a scenario of the black hole with neutrino heating. And this is a pioneering famous study done by McFarlane and Woolsey in 1999. And they show that the strong jet is launched by neutrino anti-neutrino pair annihilation that coming from the accretion disk. So accretion disk is formed around the black hole because progenitor star is rotating very fastly. And from the accretion disk, neutrino and anti-neutrino are ejected, and due to the pair annihilation, thermal energy is produced at the bottom of the black hole. And due to the thermal pressure, jet is launched. But in this study, gravity is treated as a Newtonian gravity, and honestly speaking, they did not solve the neutrino physics. So what they did in this study was to put thermal energy directly around the black hole region. Then they show that the thermal pressure drives the jet. In 2007, our group did a similar simulation, but with some neutrino physics, including neutrino anti-neutrino pair annihilation effect. This treatment is very simple, but anyway, we included such neutrino physics effect. Also, in this study, black hole gravity is treated as a Newtonian gravity. And what we found is that like this. This is the equatorial plane, and this is a rotation axis. And this is the accretion disk. And much of neutrinos is ejected, but pair annihilation effect was not so effective to drive a jet. Oppositely, matter is keeping falling into the black hole. So in this study, we couldn't find a gamma ray burst jet. But I don't want to conclude that this scenario is ruled out by our study. This is just one example. So in this condition, we cannot find a GRB jet. But if you change the progenitor star or angular momentum distribution, or if you improve the treatment of neutrino physics, maybe we can find a GRB jet according to this scenario. So there are a lot of things to do for this scenario. This is a black hole scenario with strong B fields. In this study, gravity is treated as a general relativistic gravity. Okay, so as far as I know, there are two papers that have studied jet formation using a general relativistic MHD code and with initial condition of massive star that is rotating rapidly. Okay, one is Barkov and Komisarov in 2008. They performed two-dimensional general relativistic MHD simulation with a K parameter of 0.9 with some microphysics, and they have shown that the jet is launched by extracting rotation energy of a black hole, and the rotation energy of a black hole drives the jet. But at present, the bulk Lorentz factor of the jet is still low. It's less than a few. So I think one of the reasons for this is that they have simulated their system up to 1 second after the gravity core collapse. Okay, so when the density is still too high to drive a very highly relativistic jet. So if you can perform simulation much longer, say 10 seconds or more than that, density will be lower, and this jet will be the bulk Lorentz factor of this jet should be increasing. The similar conclusion was derived by me in 2009. I also did a two-dimensional general relativistic MHD simulation with a K parameter of 0.5 without microphysics. And I also found a similar jet. And the bulk Lorentz factor is still low. Anyway, extraction of rotation energy from a black hole really works to drive a jet. This is really promising. Recently, I'm doing a 3D GRMHD simulation. The initial condition is same with 2D case. And roughly speaking, I found a similar situation is happening in even in 3D case. I would like to explain more about this simulation later. In Barkov and Komisarov and me, in our simulations, black hole is put at the center. So we did not solve the Einstein equation. Rather, we put a black hole, and by an assumption, we assume that the black hole is formed as a result of gravitational core collapse. And we put a black hole at the center, and we assume that the Kerr black hole metric. On the other hand, there are some studies on the black hole formation. Okay? In their simulations, they solve the Einstein equation, and as a result of core collapse, black hole is formed. Okay? So this is a simulation by Sekiguchi and Shibata in 2011. They did a full 2D GR hydro simulation with some microphysics, and they found that due to the rotation and the gravitational collapse, black hole and accretion disk is really formed. Okay, well, unfortunately, jet is not seen yet because this simulation is very expensive, so they cannot follow a long time scale. So now currently, black hole formation and accretion disk formation is followed by them. And a similar result was obtained by Christian Ott in 2011. They solved the full 3D general relativistic hydro without microphysics. Okay. Also, currently, they did not include magnetic field.
What is the initial condition for these pictures? What started with?
Okay. Rotating progenitor star is chosen as an initial condition, and the massive iron core is
what
formed.
mass of the core?
I don't remember exactly,
That's
but
important because the most important is this picture, the mass of core
Yes.
and angular momentum of
yes,
core.
yeah. Okay.
I think you take the small angular momentum. There is another way. If you have the angular momentum more than k parameter 1, you cannot create a black hole. This is another scenario.
Okay.
Nobody considers it.
Okay, as far as I understand, at least Christian Ott did such a simulation for various progenitor models developed by Uzley and Hager. And in most cases, they found that the black hole is not formed. Instead, core bounce happens, and the neutron star is formed at the center.
Okay.
Okay.
There is another possibility. If you have the large mass at the center core, yes, but large angular momentum, you created black hole, but not immediately during this process.
Yeah.
After dissipation of angular moment, this is another scenario.
Yes.
If neutron starts, you can formate it only the core mass less than Chandrasekhar.
Yeah. I think this is I think you are right. So this simulation corresponds to the massive core ion core model, and I think this is the direct core collapse, and the black hole is formed directly. But if you solve the less core mass case, core bounce happens, then again this explosion fails and start to accrete again, then black hole is formed. Such simulation is also shown by their paper. Okay, as for the magnet scenario, there are several simulations on the relativistic, strong jet formation. It's shown. One is Komisarov and Barkov in 2007. They solved the two-dimensional GR-MHD simulation with some microphysics. Magnet is put at the center, and they have shown that the strong jet is driven by rotating magnetar. But unfortunately, the speed of this jet is still low. Okay, again, this is because, I think this is because they could not follow the system for a long time scale, and the density is still high, and relativistic jet is not seen at the moment. On the other hand, in Bucchiantini in 2009, they have shown that, again, the strong jet is propagating, and with the Bark-Lorentz factor of 0 to 10. Okay? They have solved the two-dimensional special relativistic MHD simulation without microphysics. I think that the reason why high Bark-Lorentz factor is seen in the simulation is because they have followed the system for a long time scale. So, so they follow the system for 10 seconds or something. Then Bark-Lorentz factor is getting higher and higher, and then finally Bark-Lorentz factor reaches to 5 or 10. So if you can follow more, highly relativistic jet will be seen. This is my understanding. Again, in Komisarov and Bucchiantini, magnet was put as an initial condition. On the other hand, there are many simulations on the formation of magnet. Okay, it was presented by Sergei Moisenko yesterday, and they solved the core collapse of iron core. So magnet is formed as a result of the simulation. Okay, they solved the core collapse and with an initial condition of a massive star that rotates rapidly, and the magnetic field is amplified by differential rotation, then magnet is formed. This was done by Takiwaki in 2009. They solved the special relativistic MHD simulation with neutrino physics, realistic equation of state. But this simulation, again, becomes very expensive, so they could not follow the system for long time scale, say up to 100 milliseconds, and Bark-Lorentz factor is still low. A similar conclusion is done by our group too. Also, this is a simulation by Adam Barrow's group in 2007, and they also show that the magnetically driven jet is seen, and the magnet is formed at the center. And, but in their simulation, gravity is treated as a Newtonian gravity, but detailed neutrino physics and realistic equation of state is included. They could not follow the system for a long time scale, and since the hydro also Newtonian, so they cannot estimate the Bark-Lorentz factor of this jet. Okay, this is a review of the history of the numerical study on the gamma ray burst engine. And from now, I would like to present my recent study on the rotating black hole with strong magnetic fields by a general relativistic MHD code that I developed from scratch. And the GR-MHD code is necessary to see Brand-Hodozniak process. Brand-Hodozniak process is a process to extract rotation energy from a black hole with the help of magnetic field. And the Brand-Hodozniak process can be seen numerically now. Okay, so originally this effect was pointed out by Brand-Hodozniak in 1977 analytically. So this is an analytical schematical picture, and they assume the split monopole solution. Okay, they show that the split monopole solution, by using a perturbation method with respect to the K parameter, they could solve the system analytically, okay? And they could estimate the energy extraction rate from a rotating black hole analytically, okay? The leading term was derived by them, okay? C is the amplitude of B field, and A is a K parameter, okay? So energy extraction rate is proportional to C square. So the square of amplitude of B field. Okay, so if the magnetic field is amplified, more energy is extracted. Also, K parameter represents the degree of rotation. The range is from 0 to unity. So unity is a maximum rotating case, and 0 is non-rotating case. Okay? So energy extraction rate is proportional to A squared. This is a leading term. Okay? And 30 years later, I obtained the second leading term like this. Okay, this was obtained by Tanabe and me, 2008. Okay, this is an analytical expression. Also, so we have to assume the configuration of B field as a monopole-like. Okay. Also, since we are using a perturbation method with respect to K parameter, this analytical solution is valid only for slowly rotating black hole. Okay. So this analytical solution can be applicable to slowly rotating black hole. On the other hand, numerically, we can, of course, we should reproduce this solution if you assume the same situation as an initial condition. We can reproduce this situation. Also, numerically, we can consider highly rotating case, also with different configuration of magnetic field. Now, anyway, this is a comparison among the analytical solution and the numerical result obtained by GRMHD code. I put the same situation numerically, and I solved the system, and I checked that this system is steady. And at some point, I checked the outgoing pointing flux energy as a function of K parameter. Okay, so this is the first leading term. And this green line corresponds to the sum of the leading term and the second leading term. This is the analytical result, numerical result. Again, this is applicable only for slowly rotating parameter, K parameter, and everything is consistent with each other. So that's why I think my code is working well. Also, for rapidly rotating black hole case, this solution cannot be applicable. Rather, we should trust the numerical result. Also, again, we can study different configuration of magnetic field numerically. That's why I developed numerical code. And using my GRMHD code, I did a simulation of gamma ray burst. And this is the initial condition. I choose the fastly rotating massive star model developed by Uzure and Heiga in 2007, which has a massive ion core. And in this study, again, ion core is extracted, and the rotating black hole is put at the center as an initial condition, and whose black hole's mass was assumed to 2 solar mass with a K parameter of 0.5. And I used the simple equation of state with a power law index of 4/3. Also, I put the very weak magnetic field by putting vector potential. This gives a toroidal B field. This is very weak initially. So minimum value of plasma beta ratio of the thermal gas pressure and magnetic pressure, the minimum value was 100. So thermal pressure is much higher as an initial condition. But finally, due to the differential rotation and gravitational collapse, magnetic field is amplified, and Brandhod-Zuniac process start to work very efficiently, and jet is launched. This is a result of the simulations. This is the same simulation, but with a different scale. And This is a central region, and this covers a wider region. And this shows the density contour in logarithmic scale, and the dynamics is followed up to 1.77 seconds from the core collapse. Okay, as you see, initially matter falls onto black hole and almost steadily. Okay, but at some point, B field is amplified and the Brandford-Zoniak process start to work very efficiently, and along to the rotation axis, jet is launched. Okay, I did the same simulation but
if you come back to the initial condition, you can find that so fast rotating white dwarfs inside the usual stars cannot be exist, because the spin down, usual magnetic spin down, very quickly synchronizated this white dwarf with the body of the star. This is non-physical initial condition.
Okay, I don't know so much about the initial progenitor model, but
you take 1% magnetic energy from the gravitational energy, yes?
Initially, no. Initially, much less than 1%.
No, please, previous slide. Not before, one more. Pair gas to pair magnetic, 1% magnetic.
Yeah, of thermal pressure.
1% energy magnetic.
1% is in.
This very large magnetic field. Due to magnetic friction inside the star, this white dwarf very quickly spin down. This situation can be in real astrophysics.
Okay, maybe we should do more parametric study by using weaker case, but this is still underway.
Is the point you are making that there is going to be no rapidly rotating force? Is that the point you're making? Or you're saying that you can't have both rapid rotation and strong field? Which is the point you are trying to make?
But he wants to receive the Kerr metric with A about 1.
Well, yeah, right, that's okay.
This is impossible.
Well, but we do see in nature, after all, we do see neutron stars which are produced with rapid rotation.
Neutron star, the same problem. Nobody knows about the angular velocity of the core of the star. I think this is very slow in usual situation. This a result of the, if you look to the radio pulsar evolution, to the astrophysics, real binary system. So only in short binary system you can take the very large angular moment, but not for the white dwarf. Okay, this.
I know. Discussion. I know about because such a discussion.
The core collapse gives the GRB, but core not enough the angular momentum in real astrophysical situation.
Yes. Yeah, I know about such discussion.
You need to have the very large nuclear, like to 100,000 kilometers, 300,000 kilometers. In this case, you have enough angular moment. This astrophysical situation for the basic star, 100 solar mass in binary system.
It's a very good point, and it is a big challenge to find a rapidly rotating progenitor with strong magnetic field. So there are many discussions about that, and it's still under debate. Yes, this is my understanding. Okay, so I did the same simulation with, except for Kerr parameter. Okay, so this is the density contour at the same time slice. This is not the time sequence. This is a time slice at the same time for different simulations. Difference is the Kerr parameter. Okay, in the Schwarzschild black hole case, there is no rotation energy to be extracted. So jet is not seen. And if you go to the high rapidly rotating case, stronger jet is seen. So from these figures, it is confirmed that this jet is really driven by rotating black hole. Also, this is the most inner region of the simulation. This is a black hole. This is a rotating black hole with a K parameter of 0.95. And this is, colors represents the outgoing Poynting flux energy, okay, in units of 10 to 50 erg per second per steradian at the final stage of my simulation. So energy is really extracted from rotating black hole. So this guy, this energy is the energy source to drive a jet. Okay, so at the final stage of the simulation, I checked the jet energy. The jet energy with, within the theta of 5 degree and 10 degree as a function of K parameter. So for non-rotating black hole case, no jet was seen. So the jet energy is 0. But as you see, as the K parameter is increasing, more stronger jet was seen. And this energy is almost comparable to 10 to 50 erg. So it at the 1.1 second or something. So if we can follow the system 10 seconds or something, we can explain the GRB energy. That's my expectation. And recently, I'm doing the 3D GRMHD simulation. This is a case of 0.9 case. And this is a density contour with B field. So at 0.8 second, okay? And these are same result of the same simulation, but this is a 3D plot, and this is a slice in the rotation axis and the equatorial plane, and yeah, this is a 2D slice. The density contour with poroidal magnetic field. Okay, so initially the system is like this. So matter is infalling onto the black hole, and the B field becomes monopole-like. Okay, like this, very poroidal. But after the jet launch, around the black hole, the toroidal field is amplified little by little due to the differential rotation, and the jet starts to launch. And you can see the toroidal component. And finally, jet is clearly seen with the toroidal field, like this. Again, this is a time sequence of the simulation with a 2D slice. So this is a status at 0.35 second, and this is a 0.8 second. This is almost similar, but these are not the same figures. But the system, since the system is almost steady, these looks very similar. But after some time, toroidal field is amplified little by little. Then Brand-Photozeniak process start to work, and the jet is launched. Okay, so please remember that the Brand-Photozeniak process is power is proportional to B squared. So when the B field is amplified, Bz power is also amplified. Okay. The future study, I'm extending my code. I'm trying to attach adaptive mesh refinement technique to my code. This is the test simulation, but AMR is like this. if you need finer resolution, you can put more grids. But if you don't need fine resolution, you don't have to put fine grid system. So this is really efficient to save the CPU power. So by using this technique, I think I can do a finer resolution simulation. Also, from September 2012, the fastest computer in the world becomes open to Japanese scientists. This computer's name is K. K means 10 peta in Japanese. And this is a character for K in Japanese and Chinese. Okay, anyway, 10 petaflops computer will be open to Japanese society, and now I'm planning to apply to use this computer, fastest computer, and I would like to do the finer resolution simulation in the near future. Okay, this is a summary on the central engine of long gamma ray burst. An outline of explosion mechanism of long gamma ray burst is still under debate. There are lots of things to do. And the rotation energy of a black hole can be extracted with the help of B fields, Browne photogenic effect. And faster is better. Rapidly rotating black hole can drive an energetic GRB jet. And GRB simulations by 3D geometry code are being done, and AMR will be attached, and 10 petaflops computer will be open very soon. I think I still have 5 minutes, yeah. And so I would like to change, and I would like the topic, and I would like to show our recent study on gamma ray burst using 5 minutes. Gamma ray burst as a treasure box of physics and mysteries. So up to now, I only talked about the central region of a gamma ray burst. But after that, there are plenty of interesting topics about gamma ray burst. For example, after the jet launch, explosive nucleosynthesis should happen here. Also, relativistic jet propagates. And as Kumail's talk yesterday, there should be some dissipation, and gamma ray burst is produced here. But we don't know the mechanism. Maybe photospheric emission, but maybe magnetic dissipation or internal shocks. And if you use gamma ray burst, GRB cosmology may be possible. And afterglow is followed, and finally, gamma ray burst and supernova remnants should be produced. So we are studying these topics. Yeah. And I would like to introduce our study very shortly. Okay. First, I'd like to introduce our study on explosive nucleosynthesis in jet-induced supernova. So that includes gamma ray burst, but not only gamma ray burst, but also jet-like supernova explosion. And the calculations of explosive nucleosynthesis in jet-induced supernova were done to explain, and predict, and find these things. Okay. Large titanium-44 production that may be important for supernova 1987A and Cassiopeia A was found. And the line profile of ion for supernova 1987A is produced. And the kick velocity of a neutron star in supernova 1987A is predicted. And split line profile for highly aspherical explosion is also was predicted. And the correlation between duration of explosion and amount of nickel-56 for hypernovae were predicted. And the dark supernova associated with gamma ray bursts are also predicted. I don't have time to explain all of them, so I'd like to show you some result about that, about some topics. This is the observed line profile of iron for supernova 1987A. This is a blue shifted side, and this is a red shifted side. And you can see that the highly red shifted and blue shifted component exist. Also, the line profile is asymmetric. Okay? So as for the highly moving component, this component is reproduced by jet-like explosion. And this asymmetric profile is explained by aspherical explosion with respect to the equatorial plane. Okay, this is a result of the calculation. This is a mass fraction of nickel-56. Okay, so much of nickel-56 is produced in the jet region. These guys can explain the highly escaping component with high velocity. And we assume the aspherical explosion, such asymmetric profile is reproduced. Okay. So in this aspherical model, more nickel-56 is going to the red shift side. Okay. And due to the momentum balance, neutron star should be running toward the blue shifted side. Okay. So maybe, as you know, the neutron star in supernova 19A is not found yet. But my prediction is that the neutron star should be running toward the blue shifted side. And recently, the red shift region and the south, from the detailed analysis of line, iron line and the silicon line, it has turned that the southern part is red shifted side, and the northern part is blue shifted side. Okay, this is a blue shifted component. Okay, this is a red shifted component. So as for the blue shifted component, north is bright, and for the blue shifted red shifted side, south is bright. Okay, so my conclusion is that pulsar and neutron star should be running to the blue shifted side. So in supernova 1987A, neutron star should exist in the northern part. This is my prediction. So we are revisiting this topic by final resolution study with my postdoc, like this. Okay, this is the summary of my talk. Thank you very much.